Hey, welcome back, Marauders. This is video 3.6, Deviation from the Ideal Gas Law. So real gases don't actually behave exactly the way that they would be predicted by the ideal gas law. And the reason for that is that the molecules do take up space and they do interact with each other. Remember when we talked about in our last video the kinetic molecular theory and the five postulates. One of those was that the particles don't take up any space, but that's not actually true. Particles do have a little bit of volume. Their volume is pretty small and it's usually pretty insignificant, but it's not perfect. They do take up some space, and so that's one reason that real gases are a little bit different from ideal gases. And then the other assumption we made was that they do not interact with each other at all. They don't attract each other. That's actually not true either. The particles can be slightly attracted to each other with intermolecular forces. So these two assumptions are pretty good for most gases, but things that are large and things that are polar are going to be things that behave differently than predicted by the ideal gas law. So those like real gases will deviate the most from the ideal gas equation when they're large molecules or when they're polar molecules. The conditions where it's going to be closest to ideal is where temperature is high because the particles are moving around really rapidly and the pressure is low because there's a lot of space in between them. So for a real gas, using the ideal gas law, you'll get a very accurate answer when the temperature is really high and the pressure is really low because there's space between the particles and they're moving around really rapidly. But real gases will deviate from the ideal gas law a little bit more when the temperature is low because they start moving slowly. When they're moving slowly, they can be attracted to each other a little bit more. And then also when the pressure is high. When the pressure is high, the particles are all really close together. And when the particles are really close together, then their volume, the space that they actually takes up, becomes a little bit more significant. So this is the van der Waals equation, and you probably won't have to plug numbers in and solve anything with the van der Waals equation, but it's helpful to look at this equation because it helps us to understand why real gases are not exactly the same as ideal gases. So the van der Waals equation, it looks like a lot, but it really looks kind of like pressure times volume equals number of moles times R times T. So it's kind of our PV equals nRT equation, but with a couple corrections. There's this correction right here because the pressure of a real gas is not exactly the same as an ideal gas. And there's this correction right here because the volume of a real gas is not the same as it would be for an ideal gas. And so there's these two factors, A and B. And factor A is to account for the fact that the pressure is not exactly what we'd expect, and that is because the particles do attract each other a little bit. And so these factors A right here are going to be lowest for really small molecules that are totally nonpolar because they don't attract each other at all. And then these factors are going to be a little bit larger because you need a little bit bigger correction when the particles are larger and when they start to attract each other a bit more. And then this correction right here is a correction of the volume because the particles actually do take up space. So again, you're going to see a bigger correction factor for molecules that are larger because the volume of a real gas deviates a little bit more from what we would assume in the ideal gas equation. So again, you probably won't have to plug anything into this equation, but you should understand that real gases don't behave exactly like ideal gases, and you can correct the pressure, correct the volume to account for that difference. You should also definitely know when real gases are the closest to ideal, and that's when temperature is high and pressure is low because the particles are moving around really fast and there's a lot of space in between them.